So, welcome to the electrostatics part 3 or lecture 3. And till now we have understood electric field, we understood about electric dipole. We also got into the electric field, okay, due to dipole and different configurations. We also understood continuous charge configuration, and then we got introduced to Gauss's law till the last class. So we will recap the Gauss's law again before we go into the applications of the Gauss's law. So Gauss's law is nothing but it gives the electric flux, okay, that is there because of charge being enclosed by a surface. Okay, so first we actually divide the surface into smaller area elements. Okay, we calculate the flux through each of those area elements, and then later on we integrate them, or we sum all of those fluxes to get the final flux. So if you multiply, okay, so your E, the electric field, okay, that is there, it's going to be Q by 4 pi epsilon 0 R square. And then when you multiply the area of, say over here we are considering a sphere. Okay, so when you multiply it with the area, so what you are left with is just the charge that is enclosed by the surface or the sphere in this case, divided by the epsilon 0, that is the permittivity of the free space. So that is the this is the form of the Gauss's law, and this is the result of electrostatics that we consider as the Gauss's law. So suppose for as an example, we consider a thin infinite wire. Okay, so the length is extending to infinity on the both ends. Okay, and so we want to calculate the electric flux that is there because of this because of this wire. Okay, so you can consider the wire as a cylinder, and again using flux A is equals to E multiplied by the area. Okay, so for cylinder it is going to be 2 pi RL. So if you again put these in the formula, okay, if you remember we had talked about linear charge density. Yeah, so if you remember, like lambda is the linear charge density. Okay, so if it is going to be del Q by del L, okay, for a small line element. So if you consider the surface the linear charge density of the entire wire, so that is going to be lambda is equals to Q by L. Okay, so what is going to be your Q over here? Q is going to be lambda L. Okay, so again if you put E since we are considering a cylinder, okay, so E is going to be equal to 2 pi epsilon 0 R, okay, and then you multiply it by 2 pi R L, okay, and then you remove the common terms, and then again if when you put the Q is equals to pi L formula, okay, so what you will get is phi is equals to pi L lambda L by epsilon 0. Okay, so this is going to be your the flux due to an infinite wire, okay, that is by the using Gauss's law. So if we considered a line, we are considering a charge configuration that is linear in nature. Now if we consider a surface, okay, a plane or a planar surface, so we will try to understand using Gauss's law how will we get the electric field, okay, due to that. Okay. Electric field due to the uniformly charged infinite plane sheet using Gauss's law. Okay, application of Gauss's law. So again, using Gauss's law, we are going to consider, okay, so the net flux, if we are considering surface 1 and surface 2, okay, because this is the, the plane that we are considering. So, and your sigma is what? It's your surface charge density. Okay, if you remember, sigma is equals to Q, if you consider the entire one, okay, by S. Okay, so that is going to be, sigma is your uniform surface charge density, and we are considering an infinite plane sheet. So the x-axis is going to be perpendicular to your plane sheet. Okay, so electric field will depend on both y direction and the z direction. Okay, it will depend on the components of y and z. Okay, and its direction is parallel to the x direction. Okay, so the electric field is in this direction, and sorry, my mistake, it is not going to depend on y and z, because it's only it's directed along the x direction. Okay, and if we consider surface 1, okay, so the electric field is in the negative x direction, and if you are considering the surface 2, okay, so this not the electric field, but the unit vector that is normal to the surfaces, okay, is going to be in negative x direction for surface 1 and the positive x direction for the surface 2. Okay, so but the the direction of the electric field is parallel to the unit vector normal to the surfaces. Okay, so electric flux, as we remember, phi is given as the multiplication between the electric field. Okay, it's given as the electric the field dot product between electric field and the area element. Okay, so that is nothing but it's electric field into the area. So if we again consider small area elements, okay, and we find the flux for each area element, and then it will for both surface number 1 and surface number 2, and then you add up for all the surfaces, and even with the both surfaces, okay, so they are equal. The flux through both the surface 1 and 2 is going to be equal, and they will add up. So your net flux through the Gaussian surface that we are considering is going to be twice of the electric field, of the product of the electric field and the area. Okay, and the charge enclosed by the closed surface, as per the this formula, we can see that Q is going to be equal to sigma, that is the surface charge density, into the area. Okay, so S over here, it can be surface area, or over here we are considering the area of the plane. Okay, so again, by Gauss's law, net flux is going to be given as the Q by epsilon 0. Okay, and then because we want to find out the electric field due to the uniformly charged infinite plane sheet, we are going to get it as sigma by 2 epsilon 0. Okay, now if you want to represent it in the vector form, you are going to include the unit vector that is normal to the plane, and that is going away from the plane. Okay, so over here you can see that E is directed away from the plate if this is sigma. Okay, so S is going to be, if sigma is positive and if the sigma is negative, then it is going to be towards the plate, the direction of the electric field E. Now we come to the third application of Gauss's law, that is electric field due to uniformly charged thin spherical shell. Okay, so over here we are going to consider two cases. One where the electric field that we are considering is outside the spherical shell, and then the next one that we are going to consider, the Gaussian surface, it's going to be inside the spherical shell. Okay, so in the first case, when the field we are considering outside the shell, so we will consider, suppose say a point P. Okay, and the Gaussian surface is going to be the radius, it's going to be the radius of the the spherical shell that is there plus some distance. Okay, so the small r is going to be the radius of the Gaussian surface that we are considering outside the thin spherical shell. Okay, and the big R is the radius of the thin spherical shell. Okay, the surface charge density we are going to consider on the surface of the spherical shell. Okay, now for each point on the Gaussian surface, okay, so there is going to be the E, okay, the electric field is going to be same along the Gaussian surface, okay, and it's directed in the, along the radial direction, okay, the radius vector at each point, so R bar, okay. And hence, because of that, as we know that when we are considering del S, we are going to consider the normal vector to the surface. So E and del S, okay, are parallel, and thus we are going to consider each, the flux through each of the element is going to be E del S. Okay, so phi is going to be equal to E del S. Okay, so this is what we know. Phi is going to be like that. Okay, if we sum up all the del S together, okay, so E is going to be, as we are considering a spherical shell, so E multiplied by 4 pi r square. Okay, so again, if you put the flux, okay, E into the S, the area, okay, and also then you put E in the form of your surface charge density, okay, so the Q, and then what you are left with is the sigma by epsilon 0 into 4 pi r square. Okay, actually there should be 4 pi, there is a change in this equation. So this is going to be sigma by 4 pi epsilon 0 r square multiplied by 4 pi r square. Okay, so your 4 pi is going to get cancelled out. What you are going to be left with is the surface charge density, epsilon 0, the permittivity, and the square of the radius of the spherical shell, and the square of the radius that we are considering for the Gaussian surface. Okay, so then what we are going to write, the total charge of the spherical shell can be given as the area into the surface charge density. Okay, so again then you replace this upper term, okay, with respect to the total charge that is there for the spherical shell. So this is going to be the electric field, okay, outside the shell due to a uniformly charged thin spherical shell. Again, vector in the vector, as a vector form, you can then add the unit vector. Okay. What is important to know, that the electric field will be outward if Q is more than 0, that if it is it is positive. If Q is less than 0, that is negative. If Q is negative, then the electric field direction is going to be radially inwards. Okay, so this is how you can apply Gauss's law to understand the electric field due to an uniformly charged thin spherical shell when we are considering the Gaussian surface, or when we are considering a point outside the shell. Okay. If we consider if we want to find out the electric field at a point inside the shell, okay, so due to the presence of this uniformly charged thin shell, we find that the Gaussian surface that is inside the shell does not enclose any charge. Okay, and that is why we get E is equals to 0. Okay, so if your Gaussian surface radius is less than the radius of the shell, then we are going to get 0 electric field. So there is no charge enclosed inside the shell. Okay, so most of the charge is concentrated on the the shell. Okay, so the charges are concentrated in on the surface of the shell, and because of that we are going to we get that any Gaussian surface that is considered to be inside this shell is not going to have any charge, and that is why there is no electric field. Okay, so that means that the uniformly charged thin shell, the field due to the thin shell is 0 at all points inside the shell. Okay, this is a direct consequence of Gauss's law, and which follows from the Coulomb's law that we had defined to find out the electric field. Okay, so this is what we have understood about electric field, how electric field varies when we consider a point charge, a system of charges, and then we also saw electric field due to a dipole. Okay, and then we inferred Gauss's law, where we are trying to understand the electric flux and hence the electric field due to the presence of charge over either enclosed by a surface or it is on the surface. Okay, so this is what we have learned till now. Now we will move on to electrostatic potential. Okay, so if you remember in like previous in 11th or 11th, or when we were studying when you must have studied gravitational field. Okay, so we learn about something called potential energy. Okay, so the potential energy is it's usually the work done in moving that is stored in the body when it is moved from one place to another. Okay, so that is the basic understanding of potential energy. So when we are considering electric charges, okay, so there is a potential that is associated with them too. Now, if you remember, we had spoken about electrostatic potential, electrostatic force. Okay, so it is also conservative in nature. And it also has the inverse square dependency that is similar to what we see in the gravitational force also. Okay, and that is why it is it follows that there would be a potential that is associated with the with electrostatic charges too. Okay, so the like the potential energy of a mass in a gravitational field, we can also define electrostatic potential energy of a charge in an electrostatic field. Okay, so suppose we are considering a test charge, okay, that is positive in nature, and it is being moved from point R to point P. Okay, so you can see that this is the test charge that is positive, okay, and it is being brought from point R to point P. Okay, and there is another charge, positive charge again. Okay, suppose this is the origin. Okay, so it is we are bringing this test charge, okay, from a point R to point P, which is in the electrostatic field due to the charge capital Q, okay, which is placed at the origin. So now you can see that this is also positive. The source, the capital Q charge is also positive, and the test charge Q is also positive. Okay, so there is going to be repulsive force. Okay, but we are doing work, okay, in against the repulsive force while moving from point R to point P. Okay, so there is some amount of work that is being done. Okay, so you have an external force that we are using to move it from R to P. Okay, and there is an electrostatic force. Now, because the external force is acting in the opposite direction of the electrostatic force, it is going to be the external force is going to be negative of the electrostatic field. So what we can imply from this is that there is no net force or acceleration on the charge Q. Okay, so when it is being brought from R to P, okay, we are assuming that the speed of bringing from R to P is not causing any acceleration to happen. Okay, and also as I said, because the work that we are doing in bringing it from R to P is in the direction opposite to the electrostatic field, and that is why the work done by the external force is going to be negative of the work done by the electric force that is there. Okay, and it gets fully transformed in the form of a potential energy of the charge Q. Okay, so we are bringing test charge Q from R to P and the work is being done. Okay, the external force is doing work on the charge Q, okay, which is going to be negative by the work done, which is the negative of the work done by the electric force. Okay, and the difference or the work that is being done is going to get stored as a potential energy of the test charge Q. Okay, so now we'll see how we can mathematically represent it. Okay, so if if we remove the external force, okay, which is acting opposite to the electric field, if we remove it, the repulsive force will come into action. Okay, and it will take the test charge, the small q charge, okay, away from the q. Okay, and when it is it is moving away from the charge that we placed at the origin, the stored potential is going to give the test charge q the kinetic energy to in a way that it is going to be conserved. Okay, as we said before, the electric force that is there, okay, it's conservative in nature. So the potential energy that is stored in the test charge Q, okay, when we had brought it from R to P, okay, it is stored. Now if we remove the external force, okay, so due to the electric force alone, it is going to get pushed away from the source at from source charge Q or the charge Q at the origin. Okay, and it is going to get converted into kinetic energy, and the conversion that is happening, okay, it is in a way that the sum of the kinetic and the potential energy will be conserved. So according to that, the work that is done by the external force, we can give it as an integration of the force external multiplied by the the radial distance that is there. Okay, the not radial distance, the distance that is being covered by the charge when we are bringing it. Okay, then it is going to be the negative of the electric force, as we had mentioned before, that the external force is going to be negative of the electric force. So we can say that the work done is against electrostatic repulsive force and gets stored as potential energy. So at every point in the electric field, okay, a particle with charge q will possess a certain electrostatic potential energy. And because of the work that is being done, okay, it will increase its potential energy by an amount equal to the potential energy difference between points R and P. Okay, so the electric field is present, okay, everywhere. Okay, suppose this is where your electric field everywhere is present. Okay, so a particle with charge q, okay, it will already possess an electrostatic potential energy, okay, when it is being brought from R to say P here. Okay, okay, and the work that is being done, okay, it increases by the amount equal to potential energy difference between the points R and P. Okay, so the say the charge q had a potential difference in at point R, the potential energy, okay, at point R, and then it had another potential energy, it gains another potential energy over here. Okay, so when you come to UP, okay, so UP is going to be UR plus del U. Okay, so this is your potential energy difference. Okay, so whenever we are moving the charge from one point to another, so the potential energy, okay, is going to increase by an amount that is the potential energy difference between the 2 points. So if you rearrange the equation, what you will get is del U is equals to UP minus UR, and again the potential energy difference that is there is actually the work done in bringing the charge Q from point R to point P. Okay, and the displacement is in the opposite sense of the electric force. Okay, so as we already said, the electric force is in this direction. Okay, so the electric force is in this direction. Okay, and the work that we are doing is in the negative sense or the opposite sense of the electric force. So then the work done by the electric field is negative of the work that is being done in bringing the charge from R to P. So we can define electric potential energy difference between 2 points as the work required to be done by an external force. Okay, the work that is being done. Okay, so this is your R, this is your P. Okay, so the external force, so the del U, that is the potential energy difference between points R and P, is the work required, okay, to be done by the external force in moving, okay, without accelerating the charge Q from one point to another in an electric field, okay, for an electric field that is present due to another charge over here. Now this can be any charge. Over here we are considering a point charge, okay, it could be a system of charges, it could be a dipole. We will see how the potential varies with respect to the charge configuration. Okay, so this is how we are going to define the electric potential energy difference. Okay, the work done, the work required to be done by the external force in moving the Q, the charge Q from R to P, okay, from one point to another in the presence of an electric field due to an arbitrary charge configuration. So this work that is being done is going to get stored in the charge Q, okay, as a potential energy, and the potential energy difference is the work done to in moving the charge from R to P in the electric field. So that is the electric potential energy difference. So some of the some important points that we have to remember with respect to the equation. Okay, the equation that we are talking about is this UP minus UR is equal to work. Okay, so the right side, I'll just write the equation here again. So UP minus UR is equals to WRP. Okay, so the right side of the equation, it work only depends on the initial and the final position of the object that we are moving. Over here we are considering the charge. Okay, so work is only going to be dependent on the initial and the final position of the charge, and so what we can imply from that is that work done by an electrostatic field is also going to be depend only on the initial and the final points of the positions of the charge, and it is independent of the path taken from that point, from one point to the other point. Okay, so this is actually follows the fundamental characteristic of a conservative force. Now the equation defines potential energy difference in terms of physically meaningful quantity work. Okay, so if you kind of what we are not interested in the actual value of these potential energies, okay, but we are actually interested in the energy, in the potential energy difference. Okay, so we are not going to be concerned about what is the potential energy that is being, that the Q has at different points. What we are going to consider is the potential energy difference because of it being brought by one point to another point. Okay, so that is why the potential energy of charge Q at a point in the presence of a field, okay, electric field, is a work done by the external force equal and opposite to the electric force in bringing the charge Q from infinity to that point. Okay, so suppose you consider that your point is at, at infinity. Okay, if you consider the it being at the infinity. Okay, so suppose you from infinity you're bringing it to point P. Okay, so your work from infinity to P is going to be actually only dependent on the potential energy is going to be the potential energy that is stored in the charge Q at the point P itself. Okay, so we understood what is the potential, electric potential that we are talking about. Okay, so or you can say that this is the electric potential energy, okay, that we spoke about in the slides till now. Now we are going to understand what is electrostatic potential. Okay, so suppose we are defining the we are considering we want to understand what is the potential energy of the test charge Q, okay, in terms of the work done on the charge Q. As you can see, there could be a number of paths that can be used to bring the test charge from R to P point. Okay, so again, the work done is not going to be dependent on any of the paths, but what we see is that the easiest part that can be taken, that will be taken from R to P. Okay, so we will consider only that. So force at any point, okay, is going to be equal to the charge multiplied by the electric field. Okay, this was the starting of the Coulomb's law that we had seen in the previous classes. Okay, so E is the electric field at that point due to the given charge configuration. So your charge configuration has Q1, different charges that is present. Okay, so the electric field is going to be due to this system of charge. Okay, so and so the force at any point is going to be the magnitude of the charge, that is Q, and E, the electric field. So if we are now we want to understand what is the work done, okay, per unit test charge uh, uh, in the electric field, okay, associated with the charge configuration. So because we are considering electrostatic charges over here, so we are now going to define the electrostatic potential V that is going to be there due to a given charge configuration. Okay, so previously we had talked about the potential, that is there, potential energy of the test charge Q due to the electric field, present because of a charge placed in the origin. So now we are going to get the understanding of electrostatic potential due to a given charge configuration. Okay, so the work done by the external force, in bringing a unit positive charge from point R to point V, point R to P is going to be given as Vp minus Vr. Okay, if you remember, it is we had learned that the it's going to be Up minus Ur by Q. Okay, so this is the the force. Okay, we remember the F external, okay, is equals to your minus Fe, that is your electric field. Okay, So your Fe is going to be Q by E, okay, and considering the work done by external force in bringing, okay, so we are going to subtract the potentials that are there at each of the point, okay, and that is why we get that P and VR are the electrostatic potential at P and R respectively, okay. So from this we can imply that the work done by an external force in bringing a unit positive charge from infinity to a point, okay, if we are considering again the from infinity to a point P, okay, so that is going to be equal to the electrostatic potential at that point alone, okay. So that is the understanding of the electrostatic potential. Okay, so electrostatic potential is again related to the work done by the external forces in bringing the unit positive charge from one point to another point. So now we will talk about electrostatic potential due to different charge configuration. So in the first we are going to consider a point charge, okay. So there is going to be electric field due to the this charge Q, okay, this is a positive charge that is placed at origin, and then we are bringing a charge from infinity to P, okay, so we are bringing another charge that is again a positive charge, okay, from infinity to P. Now obviously since both of them are positive, the force is going to be a repulsive force between them, so the external work that is going to be done in bringing it from infinity to say P is going to be negative of the electric field that is present because of the charge capital Q. So we want to determine the potential at any point T with the position vector R from the origin. Okay, so for that we are going to calculate the work done in bringing the 1 unit positive charge from infinity to point P. Now for Q more than 0, as I said, the work will be against the repulsive force. Now the work is independent of the path, so we will choose a path that is like the radial direction from infinity to the point P. So before we come to point E, suppose we consider intermediate point, okay, between infinity and say P, okay, and that P prime is going to be situated at a distance of R prime from O, okay, and then if we consider that, then what we are going to, if you remember, we had suggested, okay, so the force is going to be Q upon 4 pi epsilon 0 R prime square, and in the vector form we are going to multiply by the unit vector along R prime, okay. Q into 1 is the charge that is present, okay. So the work done against this force, okay, from R prime to R prime plus del R, okay. Suppose the work that is being done to bring from P prime to this point, okay, so the difference between the distance is del R prime, okay. So and your R prime unit vector is along OP, okay, so the work is going to be negative because as you saw that R prime, okay, so the del prime is less than 0, okay, and del work is positive. So the total work that is being done can be given by integrating the equation, okay. So what we get, okay, suppose we try to understand this is the final equation, okay. So if we are considering del W, okay, del W is going to be minus Q by 4 pi epsilon 0 R prime square, okay, multiplied by del R prime, the unit vector, okay. So if you integrate this, okay, if you integrate this, So W is equals to integrate. So now we are going to integrate it from infinity, okay, R prime, okay. So it's going to get integrated from infinity to R, okay, that is up to the point P that we are considering, so that we want to find out. So you have to integrate this equation from infinity to R, okay. So then you will get the work, okay. This is all going to be del, okay, this is going to be del, and then you integrate this, okay, with the minus. So what you get with this is going to be that work is going to be equal to Q upon 4 pi epsilon 0 R. Okay, after integrating from infinity to R, you are going to get this. Okay, so this is the work done by the external force. Okay, this is done by the external work done by the external force in bringing the charge from infinity to point P. Okay, so this we have understood the work. Now using the work, as uh, I did the integration, I explained the integration in the previous slide. So using work, using the work done, we can get the electrostatic potential at point P due to the charge Q. Okay, so that is going to, the work done is equal to the electrostatic potential. Okay, we remember that the work done in bringing the charge from infinity to any point is going to be equal to the electrostatic potential of the charge, uh, electrostatic charge of the point. Okay, so VR over here is actually the electrostatic point at point P. Okay, now this is going to be true for any sign of the charge Q. Over here we considered the positive charge. Okay, so if your the charge kept at the origin is less than 0, that is negative, your potential is also going to be negative. But what that means is that the work done is also going by the external force is going to be negative. Okay, so this is kind of a corollary to saying that the work done by the electrostatic force in bringing the unit charge from infinity to the point P is positive. Okay, so if the work done by the external force is negative, the work done by the electrostatic force is going to be positive. Now one difference that you can see is that the electrostatic potential actually varies with respect to 1 by R, whereas if you remember that electrostatic field varies by 1 by R square. Okay, so this is one important distinction when we are considering electrostatic potential or electrostatic field due to a point charge. Okay, now if we consider an electric dipole, okay, so dipole, you remember that the dipole moment is going to be 2qa. Okay, q is the charge. The dipole is made up of two equal and opposite charges at the ends. Okay, so this is going to be plus, this is going to be minus, and the magnitude of the charge is the same. So we are going to only consider the magnitude of the charges. Okay, and 2a is the distance between the two charges that we are considering for a dipole. Okay, again we know that the electric field, when we are considering for a dipole, okay, it's also depending on the angle that your vector from the center of the dipole to the point P that we are considering is making. Okay, so your electric field is going to depend on this theta also. Okay, and also that when we consider the electrostatic field that is due to an electric dipole, it varies actually with respect to 1 by R cube, not by 1 by R square, that is for a point charge. Okay, so these are some of the important things that we have to consider before we start finding out the electrostatic potential due to the presence of an electric dipole. Okay, so if you put the same, you find out how much work is being done first. Okay, so we get the equation in this form, okay, where V is going to be 1 by 4 pi epsilon 0, okay, Q by R1 minus Q by R2. Okay, so what are this R1 and R2? R1 is say the distance between the positive charge Q and the point P, and R2 is the distance between the negative charge Q and the point P. Okay, so this is going to be your electrostatic potential consideration. This is the potential due to the dipole, and it is actually the sum. This is actually the sum of the this is sorry, this is V, say Q positive, okay, plus this is VQ negative. Okay, so actually this is by superposition principle, we are going to find the electrostatic potential due to the dipole. Now, if you consider the geometry, okay, so if you want to find out how much is R1 with respect to R, okay, so we are only given the the distance between the between the center of the dipole and the point P. Okay, so we have to find out R1 and R2 with respect to the the distance between the dipole and the point P. So you can see from the diagram that R1 square is equal to R square plus A square minus 2AR cos theta, and similarly R2 square is going to be R square plus A square plus 2AR cos theta. Okay, so if you solve this with the assumption that R is much greater than A, okay, and once you expand, you're only going to consider the first order term, okay. So what you get is, R1 square is going to be this, okay, and later on we actually want to find out 1 upon R1 and 1 upon R2, okay, so that we can substitute those in the electrostatic potential equation, okay, that we found in terms of only R, okay. And we also substitute the the magnitude of the dipole moment, okay, the P, as 2qa in the formula, and putting those values in the formula, what we get is P cos theta upon 4 pi epsilon 0 R square. Okay, so this is your electrostatic potential due to the electric dipole that is present. Okay, so this is the electrostatic potential that is equivalent to the work done in bringing a charge from, say, infinity to point P in an electric field that is due to the an electric dipole. Okay, and if you go further, and you over here, this is in terms of the angle is also there. Okay, this is angle dependent. Okay, so if you consider electric potential of a dipole in the vector form, it is going to be P by R square, P dot R cap. Okay, so if you remember, the dot product will be given as P cos theta. Okay, because this is a unit vector. So in the vector form also we can write it as P dot R cap upon R square, and you multiply with this constant. Okay, if we are considering the potential along the dipole axis, okay, where suppose the point P is along the dipole itself, the point P is, say, here, okay, then your theta is going to be 0 or it's going to be pi, okay, with respect to the charges. So what you get is plus minus 1 upon 4 pi E0 P by R square. Okay, so this is going to be positive if theta is equals to 0 and negative if theta is equals to pi. If there is a point P that is in the equatorial plane that is perpendicular to the dipole, okay, so then actually there is going to be no potential. Okay, so if your theta is equals to pi by 2, your V is equals to 0. Okay, so we understood the electrostatic potential that will be there for at a point P, that is there for a charge Q that is being brought to a point T from infinity in the presence of an electric field due to an electric dipole. Some contrasting features, okay, between the electric potential of a dipole from that due to a single charge, okay, it can be said that the potential due to dipole depends not just on the r, okay, we saw it also depends on the position, the angle between the position vector r and the dipole moment vector p. Okay, if it is axial, uh, if you rotate it keeping the q fixed, it is going to have the same potential as a P. Okay, the points corresponding to P on the cone. Okay, so if you are rotating the position vector about P. Okay, so suppose this is your P, but your position vector, okay, is you are rotating about P only, keeping the Q fixed. Okay, so then the cone, the potential, okay, at any point on that cone is going to be same as the potential at P. Okay, the electric dipole potential at large distance, okay, it falls, okay, it varies as per 1 by r square. But if you remember that due to the presence of a single charge, the electric pole potential actually varies as 1 by r. Okay, so this is the difference between the electric potential due to the dipole and due to a single charge. Now we'll see what would be the electrostatic potential, okay, due to a system of charges. Okay, system of charges, so there is going to be an electric field due to the presence of all these 5 charges over here. Okay, and each of the charge is at a different distance from the point P, okay, where we are trying to find the electrostatic potential. Okay, so what we will do is we will find the electrostatic potential, okay, that is by the work done due by the external force in getting the point, in getting the charge from infinity to the point, okay, due to one particular charge. Okay, so for q1 we will find the v1, for v2 for q2 we will find v2, for q3 we are going to find v3, and so on. Okay, so where R1P, R2P, R3P are actually the distances from P to the respective charges. Okay, again, we can use the superposition principle and we can, actually get the potential V at P due to the total charge configuration. That is the total, charges that are present over there as the algebraic sum of the potentials due to individual charges. So what we will get is that 1 by 4 pi epsilon 0, and in brackets you are going to have q1 by r1p, q2 by r2p plus, we are only considering suppose say 3 charges for now over here. Okay, if we have a continuous charge distribution that is given by the charge density rho. Okay, rho is what the volume charge density. Suppose we are considering a continuous charge distribution in a volume. Okay, so the charge density that's present is going to be rho, and we can divide the charge distribution into small volumes of size say del V, and so the charge for each element, each small volume element is going to be rho into del V. Okay, then we can find the potential due to each of the volume element, and we can sum, that is integrate over all the contributions, and then we will find the potential due to the entire distribution, the charge distribution that is present. Okay, and the entire charge is actually concentrated at the center of the volume that we are considering, and thus the potential outside the shell, okay, where inside which the charge is concentrated, it can be given as V is equals to 1 by 4 pi epsilon 0 q by r. if you remember the Gauss's law, you know, we were considering the R, the small r, to be outside the shell. Okay, suppose this is the origin, so this is going to be your R and this is going to be your big R. Okay, this, the radial, the radius of the shell. The electric field, as we had seen before also, is actually inside the shell is 0. Okay, so whatever electric field that we are going to consider to find the electrostatic potential due to the charge distribution that is given is going to depend on the the charge concentration on the shell. Okay, so what will this imply is that the potential is constant inside the shell, no work done in moving a charge inside the shell, and therefore equals its value at the surface itself. Okay, so there is no work being done inside the shell. Okay, so whatever potential that we are considering for the inside shell is going to be actually equivalent to the value that is seen at the surface alone. Okay, so surface is going to be, as remember, the r is the radial distance. Okay, so for considering, for finding the electrostatic potential of the shell or inside the shell, it is going to be equal to the potential that we can find at the surface of the shell. Okay, and outside the shell, okay, we can give the electrostatic potential using this formula. So we are going to end here only today. So we understood about the electrostatic potential due to single charge, due to an electric dipole and a system of charges. So we will go into potential energy and other aspects of the electric potential, equipotential surfaces in the upcoming lecture. So thank you for attending this.